Okay, hello everyone. This is Dr. Vogel, and I'm going to quickly go over some problem-solving tips for this option 3. First off, question 1. This question is in your both in your lab manual and in your electronic textbook, The Sciences. So you can look this up, look up Galileo, and it shows you the answer to this, but it's also in the lab manual. Okay, the lab manual has a graph about the distance, the types. It has a graph showing the relationship between distance and time, velocity in time, and acceleration in time. Okay, so that one's pretty easy to look up. Okay. Next up, number 2. All right, this is also taken from the book. It's slightly adapted from a different tower, but what we're doing here is we're going to use this distance, and then we're going to calculate a time. We know the acceleration, okay? So we use the known distance and the known acceleration to calculate a time using this equation, and then we can plug it into this equation for velocity. Okay, so again, these are equations just from the book. Let's use an acceleration of 9.8 meters per second squared, okay? And then there's also the 32.2 feet per second squared. So those are your two accelerations depending on whether or not you want to work in feet or in meters. 1776 feet is going to give you a meters of 541.3 meters because you have 1 meter is equal to 3.3 feet. You can look that up, okay? So then what you do is come over here and you're going to solve for t, all right? So let's do that ahead of time. Let's change this equation to where we're going to multiply by 2. So we're going to have 2 times the distance, okay, is going to be equal to at squared. So we know a, so let's get a over here too. And then we're going to take the square root, and that's going to be equal to t, okay? I'm going to let you do that yourself. Don't forget, if you use meters, use the acceleration in meters. If you use feet, use the acceleration in feet, and just keep that consistent. Luckily, seconds are seconds, so you don't have to worry about that, but make sure you use the right set of units. You can use either one. Another important thing is this V1, initial velocity. So velocity is acceleration times time plus an initial velocity. In this case, you're going to just drop the quarter from stationary, so V1 is equal to 0. You can just ignore that, all right? Once you get t over here, you take this acceleration again, and you get v is equal to at, and that should give you a velocity. But again, if you, well, actually, it doesn't matter if no matter what, your time is over here is going to be in seconds, so you can use either one of these in the acceleration again, okay? Now, with this one, I recommend you look at the video showing the hammer and feather drop. Okay, I'll post that online. It's kind of a question. This is what Galileo showed. He showed that objects of different dimensions fall in certain ways, okay? And then the astronauts went up to the moon and proved it. They dropped a feather and a hammer on the surface of the moon, and guess what happened? Okay, we can ignore air resistance, ignore friction, air resistance, and so on, okay? So again, just make sure you kind of understand what Galileo showed there. Okay, so now we get to the harder questions, all right? And what might be easiest is actually if you go to 6, all right? 6 is something that is maybe easiest to start on. I tried to follow a little bit the main form of gravity, but then we use the specific form of gravity. But let's just look at 6 here first so you know what you're doing. All right, so to convert pounds to kg, remember that 1 pound is equal to 2.2 kg, right? So this is going to give us 71.4 kg, right? And F is equal to MA, all right? So all you do is just say F is equal to 71.4 kg times A on Earth in meters per second squared is 9.8 meters per second squared. This is the G Earth from your book, okay? So now this is going to give you a number, okay? You can calculate that yourself, but that's how we use this F equals MA. Now backing up, and then by the way, these problems 7 and 8 are just permutations. I'm going to, you just basically use this mass, and it's asking you how this Saturn rocket got off Earth. So don't forget F equals MA. All right, but here's your mass. That's going to be 140,000 kg. And then A again is going to be equal to 9.8 meters per second squared. So this one's really easy. It's just a little multiplication. All right, 9 is tricky. I'm going to come back to that one in a second. So let's back up a little bit and do the more, this is a specific case of gravity or Newton's equations, and let's look at the more general cases first, okay? So everything is relative except for big G. And this question here is asking you, and by the way, I've corrected this online, but this is in meters, but this should be that. It's 1,740 kilometers, or 1.74 times 10 to the 6. Okay, so what you do is you basically you divide this number by this number, and you divide this number by that number to get the answers here. And also you multiply times 100. All right, so I'll just do this one for you because it's the hardest one. 7.35 divided by 6.02 is 1.22. And this is the beauty of powers of 10 that we worked on last week. I just come up here and I subtract 22 from 24, and I get 10. 24 minus 22 is, it's going to be 24 subtracted from 22. Okay, so that's going to be -2. Okay, but guess what? It's times 100 because we're doing the percent. So it's 1.22%. The moon is about 1% of Earth's mass. Okay, and then for this one, you can do the same thing. Don't forget to multiply times 100. All right, so here we're going to come down and calculate the gravity on the moon's surface. Okay, and again, we've fixed this. This should be meters cubed per second squared kg. That should be fixed on your sheet. But you're going to use this general equation. You got big G right here, and you're going to have, you can ignore M1 for now, but you have M2 up here. It's 7.35 times 10 to the 22, and D squared is right there. Okay, so you're an astronaut standing on the moon like that. Okay, and then this is going to be your D, the distance to the center of the moon. That's what D is. Okay, so really what you're doing is calculating this using D moon and M moon, mass of the moon and distance of the moon. Okay, so I'll set this one up for you, but you guys should do it yourself. And also don't forget to use powers of 10, because all you got to really do is then multiply these numbers. Also make sure you do units because they help you check your work. Okay, so that's your big G, and then you're going to multiply that times the ratio of M moon, which is 7.35 times 10 to the 22nd kg. And that is going to be times 1.74 times 10 to the 6th. We're going to use meters here because you can see big G's in meters. Let's use that. But guess what? We have to square this. Okay, so don't forget to square this. So when you square this number, you then divide it from this, okay? And let's say you get, I'll do this one with you, you get 3.045. But just a reminder, that's going to be times 10 to the 12th because you have 10 to the 6th times 2. All right, so that's going to be your new numerator, and then you just keep your same old denominator. You have 10 to the 22nd kg, and there, don't forget to go subtract 12 from 22. Okay, that's going to give you a certain number, and then you multiply it times that. Okay, but you can really see the power of powers of 10. All right, and then for number 5, you do something very similar, but it asks you to look up, it gives it to you. Mercury weighs this, okay, so this is going to be your mmerc. That's what you put into this equation, and then there's your radius right there. Okay, so this is going to be your D. Don't forget to square it. Okay. And by the way, if 2.5 times 10 to the 6th meters squared is going to be 6.25. Just to show you how to do this, it'll be 6.25 times 10 to the 12th meters squared. Okay, so don't forget to do those exponents, because like when this meets G, you can really see, you can just subtract 11 from 12, and then you're almost, you basically have done away with the exponential notation. Okay, we really see the powers of 10 there. Okay, so that is a quick, that's kind of some tips on 4 and 5. Let's look quickly at 5B. Oh yeah, so 5B is a challenge, all right? And we'll grade it easily. I've told the TAs to grade it easily. The sun, if you look it up, is 1.98 times 10 to the 30 kg, and its radius is 6.957 times 10 to the 8th meters. Now this is an interesting number because it's so much bigger than Earth. Okay, you can see it's not quite coming out there, but it's so much bigger than Earth, all right? So you might wonder, well, I'm standing on Mercury, and I've got this radius of Mercury, but, okay, oh, and the other thing is that's the radius of the sun, okay? This is the sun's mass, and the distance between sun to Mercury is 51.6 times 10 to the 9th meters. Okay, so there again, this number is not just one order of magnitude, but actually when you consider the 50, it's 2 orders of magnitude bigger even than the sun's radius. And in fact, 50 times 10 to the 9th is much, much bigger than Mercury's radius. So that means that the addition of Mercury's radius and even the radius of the sun to this number, it's almost negligible. It's like 1/100th of this number. All right, so for that reason, we can just call this D. All right, you can add a couple digits to D and you won't change the answer because it's so big. All right, so when you do this problem, you call it D is going to be 5.16 times 10 to the 10th meters, and you're calculating kind of you're calculating G sun on Mercury. All right, so your mass sun, just to repeat, is going to equal 9.89 times 10 to the 30 kg, and again, that's really big, and then your G is just normal. So your equation is going to be equals G, which we've used before, times M sun divided by D, this D squared. Okay, so you square this number and then divide this by this squared, and then multiply it times g, and that should give you a number. You'll have a little bit, okay? You'll have a little bit of gravity from the sun on Mercury. It's kind of impressive. All right, we've already done number 6. Kind of talked about number 7. This one is just, don't forget your mass is 140,000 kg. Now, the Apollo lunar module is this little spaceship that they flew to the moon, and I put it on here because, like, boy, getting things to a planet is easy, but getting it off of a planet is really hard. That's kind of why we don't go to more planets with people and so on. Okay. Okay, so to do this one, it's still pretty simple, but here you're going to use your G moon from number 4. Remember, well, I didn't calculate it for you, but go to number 4 and look up what you calculated. All right, and then just equals the force of the lunar module on the moon is going to equal this 16,400 kg. You could call that 1.64 times 10 to the 1, 2, 3, 4 times G moon from number 4. So that's really just a pretty simple, once you did number 4, that's a pretty simple calculation. Okay, now number 9, again, is a super big challenge, but we like to think about those astronauts up there in the International Space Station. They're weightless, right? And they talk about them being in microgravity, okay? So the fact is, most of their microgravity actually comes from the fact that they're flying around the Earth. It's not really from their distance, but let's just calculate what their distance from the Earth does contribute to their apparent weightlessness, okay? In order to do this, we need to look up the ISS altitude, all right? I'll give you a hint. It is 254 miles, and this is equal to 408.7 kilometers, right? Now, automatically looking at this number, we know the Earth's radius is 6,370 kilometers, or 6.4 times 10 to the 3rd, or 6.4 times 10 to the 6th meters, all right? But when you compare this to this, look, we're already dealing with 1 order of magnitude less, okay? 408 is about an order of magnitude less than this. So the Earth's radius primarily determines the gravity when we consider that now your D is going to equal 6.4. Remember, G is in meters, so let's use meters, times 10 to the 6 meters. That's Earth's radius, plus this, let's go 1, 2, 3 to get the meters. So this is going to be 1, 2, 3, about 408,000, 4.09 times 10 to the 5th meters. Okay, y'all understand powers of 10 and why it's so great yet? Okay, that's going to be your D. If you look at this, though, and we convert this to 10 to the 6th, this equals 6.4 times 10 to the 6 meters plus 0.409 times 10 to the 6 meters, right? All you're doing is adding a little to the decimal. So your total D is going to be about 6.8 times 10 to the 6 meters, all right? So that is how you set that part up of the problem. It says look up the altitude. We did that. All right, and then all you got to do is set the mass. Again, it's the Earth is the nearest object. That's what's controlling it. So you're going to use the mass from the previous page. 6.02 times 10 to the 24th kg. All right, and again, you're just going to do a G mass Earth. But now you're going to divide this by your D squared, and it's your D squared that is the combined D squared of this, 6.8 times 10 to the 6th meters, right? Yeah. So again, this is a pretty simple thing. Just make sure you do powers of 10, check it with your units. Okay, now as I mentioned before, the apparent weightlessness comes mostly from the the motion and not exactly from the static Newton's equation. This is the static Newton's equation, but the thing is flying around, so it has some additional effects that we're not going to go into. But if you look this up, you say, like, what is the gravity on the ISS? And you'll get an estimate. And in fact, if you do this calculation, it should be pretty close to this. I'll give you a hint. It's closer to Earth than you would think. Because if we look up here at D, it's really we only have a tiny contribution from the additional distance. So it's going to be a pretty high number right here, at least in the static. Okay, so again, this is going to be a low number because it's not even one order of magnitude, I'll tell you that. And then for this one, just take whatever your GISS is and go F equals mg, sorry, you can't see that, ISSS, like that, 160 pounds. You guys tell me, should be getting good at this. Okay, 160 lbs is equal to 72.6 kg. You guys can look this up on Google, by the way. That's how I do it. So then that's what goes in here. All right, and then GISS is from above, and this should be in newtons. Okay. All right, email me or your TA with questions. All right, and now you are a math and physics whiz.